today's speaker has one foot in philosophy and one in physics. And we invited him because we have a physics and philosophy concentration here at Brown. We're one of the few universities in the United States that has such a concentration. So do we have any members of the philosophy department here right now? Great, okay. So the philosophy department has kindly provided a reception after the talk in our lobby. And so you're welcome to join us there after the talk. But I'm going to turn over the introduction to Nina Emery, who is a professor in our philosophy department because she does today's speaker.
Thanks so much, Brad. So it's my very great pleasure to introduce Craig Callender. Craig is a professor at UC San Diego, professor of philosophy. Before coming to UC San Diego, he taught at the London School of Economics, and he got his PhD at Rutgers, which is one of the top PhD programs in philosophy in the country. Craig works on topics in philosophy of science, philosophy of physics, and metaphysics. He's written quite a bit about the philosophy of time and has a new book coming out someday soon, right? Called What Makes Time Special on the philosophy of time. He's also done work in foundations of quantum mechanics and foundations of statistical mechanics and a whole bunch of other topics related to metaphysics, philosophy of physics, and philosophy of science. So it often seems that philosophers of physics face a bit of a choice in whether or not they are talking mostly to the physicists or trying to talk to the physicists or mostly to the philosophers. But Craig is one of the sort of rare exceptions that really succeeds in talking to both audiences. So I hope you enjoy his talk. Please join me in welcoming Professor Callender.
Thank you very much. Can you hear me? Yep, okay. Well, I'm delighted to be here. I'm from Providence originally, and so it's wonderful to be back. And then particular to speak to both physics and philosophy. Well, we'll see. Nina says I do it successfully. We'll see about that. So I love the idea of having any kind of bridge between philosophy and physics. I think of the two in some areas as being that they should really be one in certain areas. Well, certainly they start off as one in natural philosophy, and then quickly became more specialized. So what I want to talk about today is, well, I have this book coming out on time, but in physics and cog-sci, but we wanted something more physicsy for this, and so what I'm going to do is talk about a couple of different programs in quantum gravity, and we'll talk about one where, so you're probably all familiar with time, having some trouble, our intuitive notion of time having trouble when it comes to special relativity and general relativity. Well, things get then change when you get to a new theory, and as we approach, and develop theories of quantum gravity, then it has different implications for time. And so we'll look at two different theories of quantum gravity and their implications for time. And but I wanted to say two things. One is, well, I hope it's pitched at the right level. So I'm trying to, talk to two different audiences. And also, if you have any other questions about time or anything like that, I'm here right after the talk, and especially students and that. If anyone wants to talk to me about other things, I'm also happy to talk about those things. Okay, a tale of two times. So, well, first, quantum gravity. What is quantum gravity? Well, our theory of the very small, quantum field theory, and our theory of the very large, general relativity, they don't fit together all that well. So, in particular, well, you should have effects. You should have quantum effects on, sort of relativistic objects when they get really small. So if you had a black hole that was really, really, really small, it was getting down to the Planck length, then you should expect some quantum effects. Also, you should expect, general relativistic effects when you think about anything with mass, circling around anything else. Like, so there should be even some general relativistic effect between electrons and the nucleus and that. But more importantly, people often think about the kind of more theoretical conflict between the two theories. So you don't have back reaction in quantum mechanics. you don't have a, so you don't have a dynamical space-time background like you do in general relativity. And you also don't have superpositions in general relativity. So if you think about the famous, Schrodinger cat paradox, where you've got a superposition of cat alive, cat dead. Well, like a dead cat and an alive cat, there are different configurations, and therefore they must have different gravitational effects as well. But then if gravity is really space-time curvature, as it is according to general relativity, then you have a superposition of two different space-times. Well, what the heck does that mean? And so there's the thought then of trying to come up with a theory that unifies, or at least makes consistent, our best two theories of the big and the small. Now, what's been interesting is that there's been a lot of dialogue back and forth between philosophers and physicists when it comes to quantum gravity. So there's been a long history of philosophers interacting with physicists, really as long as the two fields have been around. So for instance, over the measurement problem in quantum mechanics and all sorts of other areas. But when it comes to quantum gravity, what's especially interesting is that a lot of physicists, they know one of these two theories that seem to conflict with one another, they conflict, so there's something must be wrong. And so what that thing that is wrong is we don't know what that thing is. And so all these are deep, but we're looking at really very core things when we're thinking about, say, the principle of superposition and general relativity. And so some sort of deep assumption might have to go. And so there's been this sort of willingness in the quantum gravity community to consider really pretty wild possibilities, knowing that something has to go, and so try out different very deep fundamental assumptions. And for many cases, philosophers have been thinking, thoughts that were, and doing research that was relevant to some of these assumptions. And so the one in particular that there's been probably the most amount of work on is thinking about what background independence means. And so often you think that you want a physical theory with background independence or diffeomorphism invariance. What does that mean? Philosophers have been thinking about those symmetries for a long time, and so there's been a lot of dialogue back and forth between philosophers and physicists on that. That's Bertrand Russell, by the way. But even more generally, you can look outside of just what's called the Einstein's whole argument and the problem of time and quantum gravity, but you can look and see whether philosophers have been talking about time in general. And that is one of the places where things pop up a lot in quantum gravity. So most of the programs have really interesting things to say about time. So when you take these different programs and you look at this kind of clash between relativity and the quantum, then often what happens, something funky with space often happens too, but in particular time, partly because of the preferred role that time plays in quantum mechanics. And so there have been all these conferences and all these different sort of research groups between philosophers and physics. So there was one that was just recently held at the Perimeter, written about in the Atlantic, the debate over time's place in the universe. And there you can see Ellis from Hawking and Ellis and some philosophers, Janan Ismail and others there, Ashtekar from quantum gravity. So they're all there together. And I've been part of many of these conferences, and I've been part of recently a research group at UC San Diego with some mathematical physicists who work in causal set theory. So it's just been a lot of that kind of work. So now what is quantum gravity? Well, again, it's a kind of research program. And it's not one thing. There's many, many different programs. I think it's fair to say people have their favorites in that, but I think it's fair to say that each of them starts off with a kind of core, cool idea that sort of is motivating, and then they run with it and then try to develop it mathematically into hopefully eventually to be tested someday. And then, so everyone's heard of superstring theory. Probably its biggest rival, I suppose, is to the extent that it has one, is loop quantum gravity. Prior to loop quantum gravity, its parent was canonical quantum gravity. I mentioned that because that's what we'll talk about because it's simpler, and because the result I want to talk about is it can't actually be done in loop quantum gravity yet. And then causal set theory is another one. That one we'll talk about. And then there's causal dynamical triangulations, and there's all sorts of different theories. There's a couple dozen of them, really. And so I'm just going to focus then on the second and the third. Those are nice because they form this kind of nice narrative of the sort of a tale of two times. So you're wondering whether I was going to go with the cheesy theme all the way to it was the best of times, it was the worst of times. And the answer is yes. I embrace this cheesy theme. So let's start off with the best of times. So I'll spend most of the time on the best of times. Okay. Let's step back for a second. Before I introduce causal set theory, let me give a little bit of background over time. So ever since Einstein came up with relativity, there's always been this kind of backlash. And actually, I just finished reading this history book that was interesting about the backlash by Bergson, the philosopher, whom I can't understand. But there are many, many physicists at the time, and it was very interesting to see which people accepted and didn't accept Einstein's conception of time from relativity. So the many distinguished physicists who didn't, and there was all these sort of battles. It's very interesting. And so you have this kind of battle back and forth. My book partly is a little bit about this battle. But basically the battle, as far as I can see, is sort of like this. You've got, as you walk around through life and navigate through life, you've got this model of time that's deeply important to you. It's embedded utterly, intricately in your language, thought, and behavior. So everything you do, if you're speaking in English, every verb you use is indicating it, whether it's, is, will, was, the way you think, the way your preferences are weighted, all this stuff is all modeled with this kind of what I like to call manifest time, where you're thinking that there's a preferred moment, the now, and that now is a kind of global, creates a global division between the past and the future. And the past is sort of dead, done, the future open, ripe with possibility, and that this tripartite structure updates itself. Okay. But now, so hopefully you'll reflect on your thinking about time and the way you act and behave, and see that you probably have this, even if you really know that the world has instead just this kind of, if relativity is right, then the main structure is just light cone structure at every single point. There is no now. You don't need it. You don't need a notion of simultaneity either. You don't need any of that stuff. There's no dead past or ripe future here. There's just this, picture you have of this kind of, four-dimensional picture with this kind of light cone structure, which I'm assuming everyone knows what a light cone is, right? Is that okay? Yeah. Okay. And this is the fundamental reality. And if physics is right, then this conception is basically rubbish. Okay. But it's so deeply embedded in us. It makes people think that really maybe physics is incomplete in some way, or maybe wrong, or needs to be modified in some way. And so the people who are behind causal set, I meant to mention this. If you wanted to see the conflict between the two things, you could just do one of these kind of stories like Penrose does, where consider Alice and Bob. They intersect on Thayer Street as they're walking by one another. Then they calculate, what on GI 15AB is the event that's simultaneous with O, and there's a missing B there. There should be an event B right there for Bob, and so O is simultaneous with B for Bob and with A for Alice. Imagine that they, later were wondering, suppose they had to color in red on a space-time diagram all the events that were unreal when we passed at O. Well, then you quickly see a coloring problem, because what's going to happen between, what color is all that region on GI 15AB between A and B. It's either colored in or not colored in. It's either real or not real. This manifest conception of time just doesn't really hold up in a relativistic world. But that's all true of relativity. But when we move to a new physical theory, all bets are off. And so when you go to causal set theory, one of the main reasons people say to hold it, or one of the main attractions, is that it rescues your intuitive notion of time from the clutches of evil relativity. That's the idea. So causal set theory is a theory whose main developer is Raphael Sorkin, who's a professor at Syracuse, Faye Dowker at Imperial College. My colleagues David Meyer and David Rideout are also principals in this area. It's a particularly interesting theory to look at, especially from the point of view of a kind of philosophy physics bridge, because one of the main theorems it's based on was proved by a philosopher. And so it also traces nicely to the causal theory of time, which can go all the way to Leibniz, if you like. But anyway, what Sorkin says, and Dowker as well, but the quotes from Sorkin, is that causal set theory shows how the now might be restored to physics without paying the price of a return to the absolute simultaneity of pre-relativistic days. And so when you go to a causal theory, set theory talk, you'll often see this trumpeted as one of its main attractions. And so what I want to ask is, deliver on this claim, or is it, that's Aerosmith, or is it the same old song and dance? And so in particular, what I mean by the same old song and dance is this. So when, in an earlier paper a long time ago, I put forward a kind of dilemma for anybody who tries to make manifest time compatible with relativity. It's just an informal dilemma, but the idea is this. The closer it is to being relativistically acceptable, the further away it is from manifest time. And the closer it is to manifest time, the further it is from being relativistically acceptable. So for instance, you could take some structure that's relativistically acceptable. Suppose we just took, say, some particular event. Suppose you took the birth of the first McDonald's, call it Mick event. So there's Mick event. Just Mick event by itself is a relativistically invariant thing. It's an event. And I suppose I then dubbed it the now. And well, you could do that, but it would be really stupid because it wouldn't conform at all to what you think of as manifest time. On the other hand, you could find something like that fits a little bit better with manifest time, but then it won't be relativistically acceptable. So like in special relativity, what we just saw there was somebody trying to come up with a natural notion of simultaneity with different inertial frames in special relativity. If we move to general relativity, you could imagine picking, like the cosmic frame, that you would write cosmological models in. But of course, those always pick out particular observers as special, and so they're not relativistic, or not purely relativistic. And so there are all these moves. So there's a long history of all these moves back and forth between people trying to rescue manifest time in the context of relativity. And so what I want to do is see whether causal set theory gives you something really new here, or whether it's sort of the same old moves that were already made in the history of relativity. So what is causal set theory? Well, we'll just go through the basics. I want to separate the kinematics from the dynamics and make a comment about each. Really, the dynamics is going to be where it happens. But the core of the theory comes from, there was a theorem by Hawking in the early 70s, and then it was improved and strengthened by a philosopher up the street from me, David Malamud at UC Irvine. And that theorem says that if you restrict this, so you're thinking about general relativity, and if you restrict to the class of solutions that are, there's a causal hierarchy of sort of nicely behaved and badly behaved solutions to general relativity. If you restrict to the ones that are sort of medium well behaved, so that is that are what are called officially past future distinguishing spacetimes. If you restrict to those, then the set of all continuous time-like curves is sufficient to give you back almost everything. And in particular, from relation, and you can get those then from the relations of causal precedence. So just think, if you want to think of it operationally, just think of all the things that you could cause from any event to another. So if you sent out a flashlight, if you turned on a flashlight and it could hit something, then that thing is causally related to you. In relativity, it would be all the things that are light-like or time-like related to you. So anything that's traveling, any possible signal that's going at the speed of light or less. And so what's interesting is for that class of past-future distinguishing spacetimes, you can show that the relation of causal precedence will give you back, will describe everything about the spacetime except its size. So it will give you, in particular, it will give you what is, the metric up to conformal factors. And from the metric, you're getting basically everything. And so the metric is giving the space-time interval distance between all the different points. And so for past-future distinguishing spacetimes, this causal precedence relation gets you back almost everything except for size. Now here's where causal set theory comes in. So causal set theorists, they come in, and I said each of the quantum gravity theories all come with a kind of neat idea or sort of motivating sort of thought. In the causal set theory, the motivating thought is the problem with everything is the continuum. It's all about discreteness. If we go to discreteness, if we make things discrete, then lots of problems will go away. And so they think about discreteness of the spectrum of some operators in quantum mechanics, but they're also thinking about things like having cutoffs in quantum field theory and other things. And so they think, well, maybe if we just go discrete, then we'll have some kind of make some kind of progress. Now, how does that thought then fit with this result that I just mentioned by Malamud? The answer is everything. I said that you get back almost everything from the causal precedence. You get back everything up to conformal factor, which is basically the size. And so now if you bring in discreteness, and you suppose that the world comes in little chunks, and it's not a continuum, these little chunks then supply the volumes, and then with that, plus the Malamud result, you can get back a space-time. And so with the Malamud stuff, so in particular, so if you think of like the 10 different equations for in general relativity, the Malamud basically gets you 9 out of the 10 from causal precedence, and then the volume element is coming in and setting a kind of fundamental volume scale. And so the picture that they have and want to motivate is then, you thought that relativity was this continuous thing, but just like you can't really tell, if you look at a line and you see, you can't really see all the little pixels until you get up really close. That's their thinking is that, so when I back off away from it and coarse grain, then it's going to all look continuous, just like with a line, but here it's going to look like a space-time. Okay. And so the theory couldn't be at the kinematic level any simpler, because all you're doing is you're saying that the basic structure of the theory is the coset. So what they're going to try to do is build these discrete spacetimes, and then they're going to slap matter fields on them. So all I'm really going to talk about today is just the classical theory, not the quantum theory. So anyway, so you have this structure, this coset, and it's just an ordered pair of a set of otherwise featureless events related by the relation of causal precedence. That relation will induce a partial order on the set of events, just like things are partially ordered in relativity. And then you also impose local finitude. So basically that the set of points will have cardinality less than Aleph null. And so 2 will imply that the cosets are discrete structures. And what you're going to have when I introduce the dynamics, then is this kind of birthing picture of space-times being born and created with these elements coming into being. Hence, you can see this sort of becoming type picture that's behind this. Just a couple more words about the theory. So the way they're thinking about it is then a classical space-time, so with a manifold M, metric, GAB, will faithfully approximate a causal set just in case there's an injective function phi from C to M such that the causal relations are preserved. So the set there will have all these causal relations. I'll draw an arrow if there's the relation of causal precedence and not otherwise. So think of the ones that are not comparable as space-like related to that event. And so when I lift up the approximate space-time, I want to preserve the causal relations that are, more basic. And then on average, phi maps one element of C onto each Planck-sized volume. And so all the little volumes, there won't be any empty volumes. And also that the space-time does not have structure at scales below the mean point spacing. So that is, you don't want significant curvature at a scale finer than what's set by the causal sets. And so you can find such a function just with a kind of Poisson sprinkling. Okay, so it's very easy to get a thing that faithfully approximates. What's harder is their kind of fundamental conjecture, which is the opposite, where they want to show that two similar, in some sense of similar, causal sets would give rise to the same relativistic space-time. So that's a conjecture that they work on. Okay, you don't want, like if I just moved, so one element was just born space-like rather than time-like, and you don't want then all of a sudden the whole dimensionality of the universe to change or something like that. And so that's something they're working on. But what they do have is a lot of interesting work on, you have a discrete set, you don't have, so the large inductive dimension, small inductive dimension, no definitions of dimension, they say a discrete set, the dimensionality is 0. So then you need some sort of notion of dimension, so they use a kind of, they call it the Meyer dimension, which is a little bit related to the Hausdorff dimension. You need to recreate what a geodesic is, all the sort of stuff of relativity. You need to then find counterparts for that in causal set theory. How is it Lorentz invariant? We could talk about that if you want to. Anyway, okay, so that's the theory. Is it this same old song and dance? Well, at this level, well, yes and no. Okay, so on the one hand, so in relativity we saw, you could have Alice's simultaneity plane and Bob's simultaneity plane, and they're going to differ. If you try to look for the most natural counterpart of that, then you definitely have that same exact situation. So the most natural conception of a spatial hypersurface in causal set theory is a maximal antichain, which is just a maximal set of events such that any two events are incomparable. So basically space-like, so there's no arrow going between them. And so here in this causal set, you can then see there's one maximal antichain, but unfortunately then there's also that one. And so the relativistic, the fact that there's no preferred simultaneity structure in relativity is mirrored in this theory by the fact that there's no unique or distinguished maximal antichain. There is, I'll just advertise it, there's a paper that my former colleague Chris Vutrick and I wrote where we do talk about, there is something kind of interesting, which is the causal set, you can actually make rigorous my dilemma that I put up before in the context of causal set theory. So you can find counterexamples to this interesting theorem in relativity called Stein's theorem. And that is with these sets that the research group with these mathematicians, it's embarrassing how long we talked about what the name should be, whether it should be, I don't even know how they got this name now that I think about it. But we were discussing whether it should be called Hegelian sets or non-Hegelian sets. And I don't even think we're consistent in the paper whether it's Hegelian or non-Hegelian, and I don't even know why we call them Hegelian. But they're these sets that have identical relational profiles. And then what's kind of interesting is with those you can actually, even though the ingredients are just relativistic causal precedents, you can then find these structures that could play a kind of role as a kind of present or now from those. But you can also then show that if they got big, then they're improbable and also would violate Lorentz invariance. And if they're small, then they're not really good for representing our notion of manifest time. Anyway, we can look at that paper if you want. Okay, let me turn to the dynamics. So the dynamics is really where their causal set theory people are sort of putting their money when it comes to rescuing time. So I said there was this kind of birthing process that happens. Now, one problem with causal set theory is that you could show that most of the causal sets that exist in causal set land, most of them will not give rise to a relativistic space-time. And so they want to come up with this dynamics, and one hope for the dynamics is that the dynamics cut down on all those things that won't work. And so you come up with so there's lots of different dynamics proposed. Again, this is a program, not a finished theory. And so there are all these different laws of growth that are proposed. Probably the simplest for explaining in a talk, but also one of the most attractive, is this one by my colleague Rideout and Sorkin. So they prove in 2000 a really beautiful theorem. It's really one of the prettier theorems in this whole literature, where they take very minimal assumptions about what you would want from a dynamics. That it's Markovian and a few other desirable features. And then they prove that the class of dynamics is limited then to a kind of generalized percolation. And then you can take the simplest one, which would just be something like this sequential growth model, where here, all we imagine is, the world has one element in it, and now there's a certain probability that the next one born will be space-like, and a certain probability that it will be time-like. And then, so the probability for one, you can set that as a kind of fundamental thing, p, the other one, 1 minus p, and then just run that all the way to infinity. Okay. And so you have this growth, though, so you can label then the element births by the integers. And so, at the first step there, we've got 1. At the next one, we've got 2, etc. And the dynamics is written in terms of that labeling. Okay. You can also think of it, as I say there on the slide, as each new cos set is born, you can think of it as choosing a previously existing cos set to be its ancestor with a certain probability, if you want to think of it that way. Okay, so let me, first of all, so you've got this kind of birthing process. Let me make 2 comments before we go on. So you could want to stop here in some ways. So that among philosophers, they might think, wait a second, there's 2 times going on here. So there's the time of the dynamics. So you have this dynamics, which is giving certain probabilities for things to be born, and that's run with a label time, and yet the things being born are space-time, and hence time. And so you've got these sort of 2 times going on. One, the label time from the dynamics, and then the other thing in the product being time. Well, what the heck is going on there with these 2 times? There was a famous debate between philosophers C.D. Broad and Jack Smart about that you needed to make, so Smart said, you needed to make sense of manifest time, you needed more than 1 time. So you needed a time, so because the now changes, there's got to be, and changing is changing with respect to what? Time. And so to make sense of this sort of picture, then you need more than a second time. And to make sense of that second time, you need a third time, etc. Although really you just need one time to play the role for the other, I suppose. I've always been partial to that, and not just because his name is Smart. And Broad took the opposite position. So you might want to start to worry there. What I'm going to say in a moment, the way the causal set theory people think, it will make that point a little bit irrelevant maybe. The other thing I want to mention is that you can still give a block universe picture of this causal set theory. In fact, that's what I would want to do. So, if you just think of it as a kind of stochastic process, you usually think of it as a triad with a sample space, with a sigma algebra, a probability measure. Here, the sample space, to get is just all the cost sets run to infinity. And in fact, the probability measure is obtained from the dynamics, and then you put that measure over that set. And so the real picture here in a block universe picture would be, of a space of tenseless histories with a probability measure over them. So here's this history where these things percolated into existence. Here's this one where these percolated into existence, and there'd be a certain probability over all of those. So you could get off the boat right now, but let's continue on the boat because the causal set theorist really wants this. And I want to mention a kind of problem that arises. And, well, then there's not necessarily a right or wrong way to go here, although I think, well, for me there is. But so the causal set theorist wants a notion of relativistic invariance. They want a notion of general covariance. They also don't want that time in the dynamics to be a real time. So they say that time in the dynamics is fictitious. It's just a fictitious labeling and arbitrary. So it's a gauge quantity, the time in the dynamics. Well, how do you think about general covariance in a discrete probabilistic setting anyway? Well, the way they think about it is that if I start there, say at the bottom, and I go to the top, and there are multiple ways of getting there, then the probability over those paths should be the same. And so you can sort of see it's kind of like the idea because it's this kind of path independence idea. So the probability of going right or left of getting up to the top should be the same. And then, of course, they can get much more complicated than just with two elements or three elements. So they want to then think that the theory is really relativistically invariant to the extent that means something in causal set theory, because you then have this kind of path independence and this kind of probabilistic general covariance, as they call it. But the problem is, it's hard to square that then with this notion of becoming that they're pushing. So normally you would think what you want to do with your mind when you're looking at this theory is imagine, I went up, say, the blue path on the left. So the world was, one element, then there was two, and that second one, A, was time-like related to the original one, and then later B popped up, space-like related to the two. As opposed to the worlds with one element, then a space-like related B pops up, and then a time-like link gets linked to the original one later. Okay. And so you could go up either path, and you think of the world as going up one or the other paths. But the problem is, because they think that the labeling is a gauge quantity, they can't say that. So they can't. So if they actually picked one, that would be like picking in relativity. That would be like picking a preferred observer. That'd be like picking a preferred foliation. So they can't do that, and so they have to say that there is no fact of the matter about whether it's which side you went up, right? Whether it's that side or that side. There's no difference. But then that's very odd, and it's not really going to give you what you want, I don't think. Well, it's not going to give you the original sort of picture that was motivating things, I think. Think about the case where, suppose I think about, suppose I label these, so A is actually, Alice's birthday, and B is Bob's birthday. But now, and I look at level 1, where there's the coset 2, so 2-element coset. Well, what's the reality at that stage? Well, the reality at that stage is, well, what can you say? You could say that determinately it does have two elements, but not determinately Alice's or determinately Bob's, because those have to be the same. So the identity of the elements has to mean nothing for them to be the same. And so so reality at level 1 there, it determinately has two things, but what those two things are is not decided. But then it snaps into existence. Then when I go up to the next one, then it's determinate. And so I have this sort of this is the fact that determinately doesn't penetrate the disjunction here is a sort of sign of ontological vagueness. But then what's weird here is you don't have Aristotle thought the future is sort of ontologically vague, but here it's like in the middle, what's ontologically vague. So you don't have this sort of sweeping vagueness from going toward the future. Instead, you have this very odd picture. Now, Sorkin and Dowker, they say, well, no, what you're trying to do, Craig, is you're trying to insist on some kind of global hyperplane type picture, but it's really just local. But I say, well, no, that's not really true. I'm not insisting that you go on one side or the other. I just want to know what's going on at level 1. And they say, well, you need to have, what you're asking, Craig, is for some kind of super observer with a kind of God's eye view of reality. But on our picture, we don't have that. And then I think, whoa, you don't have a kind of overall picture of reality. And so they have this sort of what they call local becoming. But if becoming is actually about like what exists or what's determinate or what's real, if it's some real feature of the reality, not just like about our knowledge, then you have this really fragmented reality that's a picture. And so Dowker says, there's Sorkin says there are no super observers, which to me is like saying there's no fundamental physics or there's no basic potentially complete. So there's not even like a potentially complete theory of the universe because it's all fragmented. And Dowker says there's no God's eye view in this picture. And now I think, well, okay, you could go that radical if you want, but then we could have done that before, back in relativity. So if we wanted to go completely anti the stream of hundreds of years of physics and have this kind of fragmented reality picture, we could have just done that and just did something like said that becoming was relative to world line or something like that in relativity. Hence, I say there might be plenty of reasons to like causal set theory, but rescuing becoming is not one of them. And then, there's Dickens. It was a typo. I wrote it was the best of the worst of times. Okay. So now it was the worst of times. Okay, so this one's a little bit more directed at the philosophers, although I have one kind of point that I don't think has come up with all that much in this literature, and so I'll make that point. So in causal set theory, we're going to rescue good old-fashioned intuitive time and objective becoming. Here, the idea is, relativity just didn't finish the job, and so it's putting the last nails in the coffin of time. And so it's just getting rid of it entirely. Now, I want to advertise this move to philosophers because philosophers have often thought about there being no time. So, in fact, for a long time, and so it's been so long that there are no pictures of some of the first philosophers. So if you think of Parmenides and the One and stuff, then in some sense there's no time. Kurt Gödel of Gödel's incompleteness theorem has this famous solution to Einstein's field equations, which he then uses to argue that essentially that time is ideal or there's no time. Famously, McTaggart also has this argument against time. Interestingly, McTaggart published his paper in 1908, the same year as Minkowski published his paper. And I always say to my students, 1908 was a bad year for time because it got nailed from philosophy and physics at the same time. But the problem with all of these no-time arguments, none of them are any good. So they all lump onto time all sorts of extra baggage, and then carrying all that extra baggage, then time falls over. But what if you just took a really minimal, uncontroversial conception of time? Can you make sense of there not being time with that very minimal, uncontroversial sense? And I think there's a really cool result in the canonical quantum gravity community that philosophers haven't really fully appreciated, and then also maybe a problem there. So this is the forerunner to what's now called loop quantum gravity. So canonical quantum gravity, canonical quantum gravity has been around for a long, long time. So as soon as people started thinking about quantum gravity, it was one of the first theories, if probably not, it was probably the first theory. Here's a way to think about it. Well, wait, hold on a second. I'll say it. The neat idea here is to just quantize the gravitational field, the metric. So the idea is just do what you did for electrodynamics, do what you did for the EM field. Now treat the gravitational field similarly, quantize, problems should all go away. That's not what happened at all. Just to get the kind of core idea of canonical quantum gravity out, it's very simple in some ways, although it gets really hairy, the math. So when you first taught relativity, you're always told, never, never, never tear asunder what God or nature put together. So space-time, do not tear those asunder. But then you look in the physics journals, and they tear it asunder all the time. So all the sort of numerical relativity, all simulations, they're always tearing asunder. And so Einstein barely finished inventing general relativity, then people were tearing it apart into what they call a 3+1 formalism, where you have a spatial geometry evolving with respect to some sort of global time function. And then it's relativistic because you could do that geometry any which way, what Wheeler called the many-fingered time. You could evolve that three spatial geometry in different ways. So if you've never seen this before or thought about it before, the way a simple way to think about it is just think of that spatial 3 geometry. So it's got a metric. You could think of that as like a particle evolving, and then you could imagine quantizing it. Except now it's not a particle, it's space. And you're quantizing the metric over that space. And if you want, you could make it really simple. You could get rid of you could just think of that space as the scale factor from cosmology, which gives basically the radius of the universe. And then that is then the sort of fundamental variable that you're dealing with. And then you're quantizing it. And so the picture then is this picture of these sort of spatial metrics evolving, and then you're going to quantize that. Well, you do so, and you end up with this equation that's famous called the Wheeler-DeWitt equation. And so what you wanted was, so H there's a Hamiltonian, and psi is now this functional, but a wave function over the spatial metric and any other matter field. So usually people just put like a scalar field or something for simplicity, equals 0. What you wanted was something like the Schrodinger equation, which is H psi equals I H bar derivative of psi with t. And so here on the right-hand side, you don't have any t, you don't have any I either, which is depressing. And so what the hell does this mean, H psi equals 0? It's almost like a bad joke, like like the Douglas Adams, meaning of life thing, where you get the answer 42. So here you used your tried and true quantization procedure, and then you get 0. It's depressing. And in particular, it's not just depressing; it also seems, on its face, to fail to describe, anything, because you have what's called the problem of time, so you don't have any temporal development. You also have the problem of what's called the static formalism. So if you adopt the quantization procedure that you would normally do, then the Wheeler-DeWitt equation is actually a constraint. And if you adopt what's called the normal Dirac procedure, then your observables commute with the constraint. Here it's now would be commuting with this Hamiltonian, which doesn't change. And so what observables would commute with things that don't change? Well, mostly nothing, except for constants of the motion. And so you get this kind of static formalism. And so then people think, well, what do we do? And so there are all these different programs inside this program of trying to deal with this. And so what I want to mention is what's called the semi-classical time program. And for those who, I'll mention it in a little bit of detail in a moment, but just so you get the basic insight anyway, the idea is that the world itself is timeless. The Wheeler-DeWitt equation is right. But when you break it up into subsystems, from the point of view of a subsystem, there's time. So other subsystems can act as clocks for other ones. Not all of them, but some. And so time emerges, if you like, from breaking the world up into subsystems. And if you think, in terms of physics, and you think the relationship between time and energy, you also could have a system, where the total energy was zero, but for the subsystems was not. And so it could be that there's temporal development from some point of view of some of the subsystems, but then not from the point of view of the whole. And so it's a beautiful idea, and so it's kind of in the background. It's kind of there in loop quantum gravity, but then the actual derivation I know is in canonical quantum gravity, and it comes from different sources. So I have here some of the names. You sort of see it a little bit in DeWitt. Julian Barber and Klaus Kiefer, whom I know, Kiefer still works on it. But I came at it from Thomas Banks, who's a quantum gravity researcher at Rutgers when I was in graduate school when I was in graduate school. And he wrote a really beautiful paper and a really beautiful derivation, and that's where I know it from. And the idea is that you take that Wheeler-DeWitt equation, and then you apply certain approximations to it to get an approximate solution. And so you're applying approximations that you may be familiar with, so things that are kind of like the Born-Oppenheimer approximation, kind of like the WKB approximation. And you're noticing that you can expand in powers of mass, and then you can get this solution, with an approximate solution, where you've got S, which is the action for the Einstein-Hamilton-Jacobi equation, and then psi, in terms of quantum, which is your quantum field, and then I've just got a scalar field there. H is the spatial metric. And so you can separate out like this, just like you can separate out, say, if you were doing the Born-Oppenheim thing, you could separate out, say, the things for the nuclei versus the electrons or that. And so you get this kind of picture of this. And then what's interesting is you note that if I look at that equation and I sort of am imaginative enough, then I notice that if I just were to treat this, which is spatial derivatives, like a DDT, that these spatial derivatives basically play the role of time. And so suppose I came at this theory with just a very minimal conception of time, where I just say time is that which I would want to say evolves, but evolves is a temporal word, that which has the pattern of correlations such that it's consistent with the pattern of correlations described by the Schrodinger equation. So imagine I write the Schrodinger equation and I pull out time, and then look at that those functional variation that's there. If I then look into this space and I see that functional variation, then that is time. That's what it is to be time, is to play the role of time. What it is to play the role of time is for the matter fields to have a pattern of covariation in accord with the Schrodinger equation. And so I don't beef up time too much. And then, if I imagine that, then what I'm having then is that for the quantum fields, I have then this time. What I'm sort of doing is I'm thinking, well, the gravitational stuff is sort of like heavy and slow, and I'm pulling out the light stuff, the quantum stuff. And so from the point of view of the light stuff, the heavy stuff is acting as a clock. And so that's where sort of time emerges like a rabbit out of a hat. But at the fundamental level, there is no time. Okay. So I think it's a beautiful idea. It's really cool of how, because you try to get your head around the idea of how, there could be a fundamentally timeless world that you keep hearing about in quantum gravity. And here's a nice kind of rigorous derivation of how you could, have a fundamentally timeless world, but then also from the point of view of subsystems, also still have the matter development that we would expect from quantum mechanics. Okay, and all I want to make, I just want to make one point, which is that there are a lot of assumptions in this, and I don't know if anyone's really thought too much about whether time gets into the assumptions. And so time won't get into any of the assumptions mathematically, because the theory itself is all time, there's no t in it, there's no time in it, so none of the assumptions will explicitly pull in a t. On the other hand, there's a kind of background justification for the assumptions, for the approximations. And if the only justification for that approximation is using time, then there may be trouble there of having smuggled in time to get time out. And so maybe so if you look at the sort of assumptions, so that there's a paper I could refer you to with, it pulls out all 20 plus assumptions, so a lot of them are big. But if you think in terms of, here's the example. If you just think of, say, in terms of the Born-Oppenheimer approximation on nuclei and electrons, you might discard the nuclear kinetic energy. Well, why? Because the answer that people will say, if you ask them in the street, well, not many people have an answer in the street, but depends which street and which hallway, I suppose. But they would say something like, heavy nuclei move slowly compared to light electrons. Well, move slowly, that's time. So you've just smuggled in time. And so if the justification for the approximations to get time out are all justified by using time, well, then I don't know what to think, really. I want to just make one comment, which is, I don't know what to think. So it's a little bit like, Wittgenstein, climbing the ladder and then kicking the ladder away. And then I think, well, that's kind of above my pay grade. I don't know what to think about that. But it seems, on its face, it seems problematic. I just wanted to mention a similar sort of thing, very, very similar, the more I thought about it. Forget the Maudlin thing. This Baker paper. So Baker shows, people have heard of the Everett interpretation of quantum mechanics, right? So it's deterministic, this sort of many worlds picture. One criticism of it is, where the heck does the probability come from? And then they say, well, the branches decohere. And then Baker says, but decoherence is a process in time. Decoherence requires probabilities. So it's probable that they'll have the branches. But now you've gotten probability out by putting probability in. Now, those approximations are very much similar to sort of saying that, at a certain scale, the world decoheres. Think of the connection between probability and time. Then in some sense, you have the same kind of thing. So the semi-classical derivation of time assumes decoherence, which assumes time. So you have a similar sort of, it might be that it makes sense, as a kind of package deal. All at once, you just interpret this as time and that as probability, and it all is fine. I'm not sure. Anyway, that's it. The conclusion is killing time is as hard as saving it. That's it. Oh yeah, I mentioned this briefly, but I should have stressed it more. Is that I was just focusing on the classical version. The hope would be that, you know, obviously if it's quantum gravity, the hope would be that you have a quantum dynamics, which would, you know, take over for the percolation dynamics. But I have to say it is a bit there haven't been as rich a set of developments when it comes to they'll throw a relativistic matter field on the resulting space-time. But what we'd really like is sort of how that thing affects the underlying discrete discrete structure and vice versa. But there hasn't been that much work there.
Any other questions? Yes.
So if I understand what you're saying correctly on the slide where you showed the larger and the smaller one, the idea is that the larger ones are going to be having less of this correlative time because, like, in virtue of being larger systems, right?
You mean on this past slide?
Yeah.
Yeah.
In virtue of being larger systems, they have less of that, like, passed on value.
Well, it's in virtue of this that I can make the approximations such that I can write the wave function as this with this approximate solution, such that it looks Schrodinger-like.
In order to get it to equal zero, though, would the heavy ones have to be infinitely large? Would the Hamiltonians end up equaling zero?
I'm not sure because this is only approximate solutions, so I'm not, and it's only. Say that again. Which?
So if we wanted the Hamiltonians to end up equaling zero, so like I and h bar aren't going to end up equaling zero, so I would figure for the d psi dt would have to be zero, right? And then that would mean that the sign off would have to be zero, right? So would that mean that it has to be infinitely large in order to have that?
I'd have to look at the derivation with all those assumptions to see. I'm a little worried about just going back from the final many stepped thing. I don't think so, but.
I have a question. So in the different models of time we presented, there doesn't seem to be emphasis on the arrow time. But there are particle experiments involving K mesons, which seem to indicate that there's some built-in arrow time. Is that an important clue to this, do you think, or not?
I mean, it might be an important clue. It depends to what. I mean, so these programs don't think of it as, I mean, they don't mention it. And when you think about the direction of time, so in philosophy of physics, when people think of the direction of time, then they're thinking about, you know, entropy increase. And then it doesn't seem to be relevant for that either. It'd be very surprising if K meson decay was the cause of coffee, you know, going to room temperature or that. But it could be a deep thing. I mean, it does seem to indicate then that, well, what's causing, you know, the mesons to know which, you know, which direction. And so it seems like you have this law-like built-in, you know, so people always would say that classical mechanics, quantum mechanics didn't care about the direction of time, but it does. And that seems really like big news and interesting. But I haven't seen anyone actually sort of use it as a clue.
Nina?
Oh, that's one there.
So if there's no time at the fundamental level, then what kind of time do we want to recover at the emergent level? So you showed a quote from Sorkin where he said that this is an advantage of causal set theory. You get time out, but it's time without absolute simultaneity. So the thought there, he seems to be very motivated by the
So you're imagining a position that says physics is incomplete with time when it comes to time? So really the manifest time is right,
Yeah.
but physics is just getting, you know, partial picture of it.
Manifest time is right about time. So time really is the way time appears to us to be. It's just a non-fundamental thing.
Oh, it's a non-fundamental thing.
The fundamental stuff that gives rise to time as manifest time. Another way of putting the question is, so if you
Yeah.
you know, canonical quantum gravity, what should an atheist about time think about canonical quantum gravity? Should they be happy because look, we eliminated relativistic space-time. There's no time at the fundamental level, so now we can just recreate time at the non-fundamental level in whatever form we want.
Yeah, so I guess, well, it would depend on the atheist's commitments to how those preferred slices interact with the stuff of the world. So if you thought that it intersected with, that it overlapped with, say in that emergent one, suppose you thought it overlapped with, so different increments of this now overlapped with the t equals constant slices according to that t. Then this would be getting you that in a sense. If it didn't, then this kind of emerging of time would be not. So then the atheist would have to do something else like this in this spirit, but not this.
Yeah, I wasn't sure the extent to which this way of getting emergent time back out was motivated by specifically wanting to get relativistic time back out as opposed to.
Oh no, it's more you wanting to get quantum time out, and so well, it'd be interesting to then think about how that was relativistic, because that is then picking out a particular foliation.
I'm afraid we've run out of time, but if you have more questions, please join us in the reception, and I'm sure Professor Callender would be happy to answer them.
Thank you.